Hello, is it being recorded now? Can you see?
Yes, sir.
Yes, sir.
Okay, thanks. Okay, so good. So it will be good if you can. If I will encourage you to go and uh, polish up your graph theory. Uh, that will be required. So all the kind of basic definitions of graphs and so on needs to be. Yeah, you should remember those basically. So so let me start with the most simplest of the graph algorithms, and mm, we will see it. So what is it? So yes, you have been given a graph, say a vertex and the edge, okay, and it might be directed or undirected. I don't know. Okay, so let's start with an undirected graph. Now, if I'm say, imagine that you are in a so you have a graph, and in which in one node of the graph something is kept. Okay, you don't know what is that or where is that, which node. What do you do? How do you find it? Okay, if one of the most obvious thing to do or most important thing to do when you have a graph is basically you have to walk along the graph and try to find it. Okay, you have to search a graph. Search a graph. Meaning, what do I mean is that maybe I will use another word of it. You have to traverse the graph. I mean, somehow come up with an algorithm to go and visit each node of the graph. And even not only each node, maybe even each edge of the graph. Okay, how will you do that? Okay, I'm not telling you any particular thing. I'm just saying that come up with an algorithm so that I'll give a graph and you have to go over all possible edges and all possible edges of a graph and all possible vertices of a graph. Yeah, how will you do that? Is the problem clear? Yeah. Hello.
Yes, sir.
Somebody was asking something. Shubir Das, you are asking something.
No, sir.
Okay. Okay. Good. So, okay. So before I go on, let me ask you an important question. How with a graph given? The graph has to be given to an algorithm, right? Has to be fed into a computer. So have you guys written any program related to graphs? Hello. Have you guys written any programs related to graphs?
No, sir.
No, sir.
No, nothing. Not even in your the programming language courses and whatever stuff like that.
Yes,
Nothing,
yes.
right?
These people have done some of the graphs. I think we had
Sorry,
in the CLab course we had done a bit.
in the which
One,
course?
I mean computer lab.
In the computer lab course, you have done some graph stuff, but that course not everybody took, is it?
I think so. Yeah.
Okay. So anyway, so can you say whoever has done it or whoever has not done it? Can you say how can you give a graph as an input? How do you feed a graph as an input?
Adjacency matrix.
Ah, so this adjacency. What is adjacency matrix? Okay, so input. What is an input? Input. Okay, so how do you give an input? So one way of writing this graph is, so they say the vertices are v1 to vn. Okay, and I have these edges. So this is v, and edges is a subset of v cross v, right? So I can think of it as a big matrix where I have the rows connected to v1 to vn, sorry, the columns, and the rows also uh, has been ordered into v1 to vn. And now, okay, what do I do? Each entry, okay, so this is called an adjacency matrix, a G. So Gij is 1 if,
Sir,
yeah.
why E is a subset of V cross V? It is
Okay,
undirected.
what is edge? Yeah, sometimes what?
It is undirected, right?
It is undirected. So yeah, it's undirected. This is, so what is what is an edge? Edge is a pair of vertices, right?
Not exactly pair of vertices.
Okay, what is edge then?
I mean, it can be single vertex as well.
It can be a single vertex. It can be like, okay, you mean like this?
Yes.
Yeah, it can be. But even then, this can also be thought about as a pair of vertices.
How do you differentiate between V and W and V? Like, there is no distinction here, right? For undirected.
What is W?
Like given two vertices like V1 and V2, ordered pair V1 and V2, and ordered pair V2 and V1.
Yes, I'm so.
That should
So
not
no.
have any difference.
So see here in this way, if you're writing as this one, then there is a difference between V1 and V2 and V2 and V1.
Yeah, but
Right? Now that is for directed. Okay. Now if I guarantee you that this set E has the extra condition that it is reflexive, which basically means that if V1 and V2 is in this set E, then V2 and V1 is also in the set E. Okay, then this set becomes an undirected graph.
okay.
Right? I mean, it's a property of the, I mean, any edge can be thought of as a pair of vertices. Any edge, even if you have an edge like this, okay, this edge can also be thought of as a pair of vertices where you have V and the edge is V comma V. Okay, now in terms of undirected and directed, it is in the property of the edge set, not in the property of a, or not in the definition of an edge. If the edge set is such that if UV is there, then VU is also there, kind of stuff, then it is undirected. Okay, I mean there are other things, but we will be mostly focusing on what you can think of as, I mean, this is something, it's called a simple graph. Okay, this is important actually. I mean, we might be at some point of time be talking about non-simple graphs also. But what do I be? So what is a simple graph? A simple graph is something where there is no self loop. Okay, so simple graph meaning this kind of things are not allowed. Okay, in a simple graph, the following is not allowed. The following are not allowed. Okay, what all things are not allowed? Self loop is not allowed, and also between two vertices, okay, multiple edges is not allowed. So this is not allowed and this is not allowed. Okay, so that means between any two vertices there can be only one edge. Okay, now it can be the directed. I mean, we can talk about it a bit later about direction and all those kind of stuff, but this is, I mean, allowed, but not, I mean, at least in the undirected case, this is not allowed. Okay, so usually you will hear this term called simple undirected graph. So simple undirected graph is exactly that. It is an undirected graph and it is simple. There is no self loop, there is no multiple edges. Okay, fine. Okay. So now the one way of writing this, representing this graph is through this matrix. Okay, and basically what I do is that this matrix is a 0-1 matrix in which G of ij, the ijth entry, okay, so there is Vi, there is Vj, the ijth entry is 1 if Vi, Vj is in the set H, in the H set, and 0 otherwise. Okay, so this is an entry. So this is a, okay, is it clear? This,
Yes, sir.
so this is called an adjacency matrix. Okay. Now, can you say that can I use this adjacency matrix to represent a directed graph? Yeah, I will ask some people. Mahesh Reddy, are you there?
Hello, yes, sir.
Yeah, can this adjacency matrix be used to represent a directed graph?
No, sir.
No. Why not?
So the thing is, Vi Vj would be the same as Vj Vi in this thing.
Why? Why will it be the same as Vj Vi in this thing? See the,
Why? Wait, I mean,
sorry?
yeah, no.
The ijth entry is different from jith entry,
Hello.
right?
Yeah. Yes, sir.
So what is V of gi? G of ji, J of ji. What is this one? So this, by the same definition, this is 1 if Vj Vi
Belongs to E.
belongs to E and 0 otherwise. So these two statements are not same, right?
No, sir.
One I am saying is that, okay, say the like 1 2 entry, I mean, G12 is whether there is an edge between edge from the first vertex to second vertex. Then I will put the G12 as 1. And G21, when will I say it's 1?
When there's a edge from 2 to 1.
When is the edge from 2 to 1? So this
This
thing
can be used for
sorry?
a directed graph.
Sorry?
So then this matrix can be used for a directed graph.
This matrix can be used for a directed graph.
Okay. Yeah, sorry, I mixed it up there.
Okay. Okay. Mayank Deora? Mayank Deora, are you there?
Yes, sir.
Can you tell me
Yes.
that if the graph is actually an undirected graph, is there any special property of the graph, of the matrix G?
Sir, it will be symmetric.
It will be symmetric, right? So if so if G is undirected, then G, what is it? Then Gi equals to 1 if and only if Gji equals to 1, which means that G equals to G transpose. Or in other words, if I just flip this thing like this, flip this matrix like this, I will have a different thing. Okay. Okay. Now let me ask you one more person. Ruksha Mitra.
Yes, sir.
Yeah. Can you just say how big is the graph of the if the graph has n vertices? Okay, so G has n vertices. How big is the adjacency matrix?
How big?
Sorry.
What is the question? How big?
How
Big.
big? How big?
Oh, acha, how big? N vertices. Then n cross n.
I mean, n cross n is the matrix. So how many entry points are there?
How many entry points are there?
Yeah.
In the matrix, there are n cross n entry points.
Okay, I mean n square entry points, right?
Yeah, n square entry.
Yeah, right. So the matrix size, okay, okay. So say I have a graph G, okay, and in the graph G, how I have the size of the vertices. So this is V cross E, is n, and size of E is m. Then the size of the adjacency matrix, C matrix, is n square. Okay. Now, okay, good. So we have got something. So here is a way of representing a graph. I have a graph. I can represent it in as an adjacency matrix, and I can fit that adjacency matrix to a program or computer algorithm, whatever. But there is one problem. The problem is that, say I have a graph which is this graph. Okay, this is a straight line. Okay, so say I have n different vertices, so v1 to vn, and the graph is this one. How big will be my adjacency matrix? How big will be my adjacency matrix for this graph? Shiva Kumar, are you there? Hello.
2n minus 2.
Who just gave the answer? Can you just say?
Sir, 2n minus 2. Since this is undirected.
This is undirected. Why is it 2n minus 2?
Sir, here v1 and v2 have a age, and also v2 and v1 have an age.
Exactly,
So,
good point. It is not 2n minus 2, but I can see what you are saying. I have a big n cross n matrix in which number of 1 is only in. So how will this thing work? There is the edge from v1 to v2, right? So 1. There is the edge from v2 to v3. There is the v4 to v4, and so on. It will be an 1, and if since it is undirected, it will be kind of a flipped along the diagonal, and in the middle there will be 0. Okay, and the rest of them will be 0. So this graph, although it has a size n square, but it has just 2n minus 2 number of ones in it. Okay, so this is not a very good idea. Why? Because the graph is small. The graph is a very simple graph, right? And yet, to feed into my computer, I have to fill in a matrix that is massive. Okay. And that is not at all a very useful thing. The difference between n and n square is a lot when n is a big number. Okay. So while adjacency matrix is a good way of, is a nice way of encoding a graph, it is not necessarily the most efficient way. Because if you have to come up with some idea of how to express, I mean, is there any other way of say inputting this graph? This graph, right? Is there? So Zemsi, are you there? Zemsi, I mean, is it your name or Zemsi? Zems, I don't know. Who is this person? Hello. Am I connected?
Yes, sir.
Okay. Do anybody know? There's someone called James in this meeting right now.
Yes, sir. He's our classmate.
Okay, James,
Maybe
right? What is
facing
his
some
name?
internet issues.
Oh, he has some internet. Okay, no problem. Then let's see. Whom can I ask? Manish?
Yes, sir.
Yeah. Can you tell me, can you think of any other way of inputting this particular graph other than the adjacency matrix? In a
Other than
slightly more,
adjacency matrix.
huh?
Other than adjacency matrix.
Yes. The adjacency matrix is a big one, right?
Yes, but we can reduce the number of entries at least.
How?
We can only take the upper triangular matrix or the lower triangular.
Oh, right. So we can know because it is adjacency matrix, so you can only give the upper triangular matrix. That's a very good point. That's a very nice thing that we don't need to give the whole matrix because it's undirected. So all is good enough to give one side of it. Okay, so very nice. That is a very good point that you can only give the upper one, but see, that does reduce the size, but it just reduces the size by a factor of 2, right? The size therefore becomes
Yes.
n into n minus 1 by 2. It becomes. I mean, you can forget the diagonal, which is always 0, say, and you are only giving the upper triangle. But n into n minus 1 by 2 is basically also again order n square. It's any other way where we don't have to kind of deal with an order n square algorithm or n square size. Manisha Panda, are you there?
Yes, sir.
Yeah, can you think of something?
Can we give entries for the vertices vi plus 1?
vi plus 1. Ah, so I mean, can you elaborate a little bit more?
I mean, in this particular graph, there are edges between vi
and vi plus 1.
vi plus 1.
Right.
So we can give entries for only those edges.
I mean, entries in terms of the entries on the adjacency matrix? Okay, not necessarily, but you are kind of thinking in the right direction. What happens if I just
Adjacency list?
yeah, I mean, that's what I'm coming towards, but for people who are not familiar with it. So one thing that we can do here is that I can even give the set E completely. What is the set E? Set E is nothing but, I mean, if I think of this, it's like V1, V2, V2, V3, right? So Vi plus 1, and Vn minus 1, Vn, and that is my list. So why don't I give this list? I mean, why don't I give as an input this whole set itself? And that set, how big is this set? How big is the set of the size set? This is in this case n minus 1, but in general it is of size m. Right? So of course you can input the graph as just this set of edges, and that's it, and that is order n. Right? There is one problem with this set. Okay, when somebody gives you a set of edges, okay, it is in a very bizarrely ordered way. So maybe so in this case of this line graph, I could have given you a set, right? This could be my entry. Okay, so say if n equals to 5, my entry can be 1 2 2 3 3 4 4 5, or my entry can also be 1 2 3 4 4, 5, 2, 3. See, these two sets are same sets. You agree? But somehow, if you were looking at this set, you understand that easily this is a line graph. But this set, because it has been jumbled up, it is not obvious what's going on. It is in a kind of very unordered way. So although these two sets are in fact telling me the which graph I'm trying to encode, but it is not exactly helping me in some sense. Okay, so another thing to be done is what is called, is basically it's called an adjacency list. Now, what is an adjacency list? Is basically nothing but you can think of these vertices as being stored in an array. Okay, one after another. And for each vertices, okay, I have another, from each vertex, I have another link to another array. Okay, so V1 has a link to another array, Vi has a link to another array, Vn has a link to another array, and so on. And what is stored in these arrays? In these arrays, what is stored are the set of vertices to which there is an edge from V1. So it will say, so all of these are all the neighbors of V1. These are all neighbors of Vi. This is neighbors of Vn. And of course, they can have different sizes, right? So at the end, I have a kind of a universal symbol which says, oh, okay, now there is nothing. So I'm not saying that all the arrays are of same size. They can be of different sizes. Okay, and this array is of size n. And this is my whole graph. Okay, is this clear? Is the adjacency list clear?
Yes, sir.
Okay, so let me see. Aditya Shankar Pal.
Yes, sir.
Can you tell me how big is this? What is the size of this adjacency list?
Sir, the size of the pointer array will be of n, and the neighborhood will be of size equal to degree of that vertex.
Very good. So this is of size n. This is of the size of the degree of
V1.
Degree of V1, right? And so on.
Yes, sir.
And now, so what is the total one?
Sir, total will be n plus summation degree of Vi.
N plus summation degree of Vi. Vi is in the set A. What is this quantity?
Okay, 2e.
Yeah, so you remember this one? That summation of degree is equals to twice the number of edges. So this is V plus twice M. Okay. This is the size of this vertex. So see, the adjacency matrix was giving us a way of representing a graph, but that was in order n square. This is allowing us to represent a graph, and that order is basically order of what we call n plus m. Okay. Now from now on, and this is the minimum that you have to write, because and graph has m information and n edges, right? So always when we think of it, so when the input, when I say that, okay, when the input is a graph, okay, without loss of generality, not this is not, it's not actually without loss of generality, but I will say that unless otherwise stated, unless otherwise stated, the size of the input, so this is graph G equals to VE, the size of the input is ordered size of V plus size of E. Okay, the graph has been given as a adjacency list. We will always assume that. Okay. Any questions so far?
But here, like repeating ages is happening. Like, okay.
Repeating edges meaning?
Like degree of V1, suppose V2 is a neighborhood of V1, then here V2, and again in the V2, we are writing V1.
Exactly. We will have that.
That
So that's
will not affect on anything or something.
That is why the 2 is coming.
Okay, okay, I got it. The 2 is coming, but like, can we reduce it or something?
You can reduce it even further, possibly. Okay, but again, I mean, this is something that you should always remember in algorithms. Most of the time, we are not too much worried about a constant multiplication and all. So that's why we use the order notation and all those things. Okay, a quadratic blow up is bad, but an order or a theta kind of stuff, right? So n plus 2m and n plus m, the base would have been m plus m. We are getting n plus 2m, so it's not too bad, and this helps us. This is way more structured than this, right? I mean, than just giving the set E. This one is way more structured, because this one is like, okay, I can just, if you tell me that, okay, now there are a lot of things that can be done. I will in the next assignment or problem set, I will give you all of that. Okay, so let me kind of tell you that, say, what is an ideal graph input? Okay, ideal graph is that I have not told you anything about how these things are ordered. So once I have given you this set, right, V1 to Vn, I can think that it is an ordered set, meaning V1 is less than V2 is less than V3 is Vn. Now, can you guarantee me that, okay, in Vi has an edge to V1 and then V5 and then V10? Is this how it should be given? But what happens if I give you the opposite? If I give you that it is given as V10, V1 and V5, I have not told you anything about the order within itself. I can give you any order, right? Okay, so I can say that, I mean, an adjacency list is perfect if within each of them it is ordered. Okay, right?
Yes, sir. Okay.
Now, this is a good thing. Why? I will tell you why. Okay, say if I give you in this set, in this just as a set system, okay, and I ask you the most basic question in a graph I can ask you is that, is there an edge between Vi and Vj? How will you check it here?
Like, I will scan through the element. If Vi, Vj is they belongs to E, then
yes, you will scan through the whole thing, right?
Yes.
And then you will take a decision, right?
Yes, sir.
So the total worst case runtime will be order M. What about here?
Okay, I will only like only n, like n and then degree of Vi.
Not even n.
No, yeah, okay.
I know
and
Vi, right? I will go straight to Vi. It's an array, right? I know the ordering, so I can just say, okay, I'm telling you, is there an edge between V30 and V100? You will just go to V30
Okay.
and look at its and look at its this thing, right?
Yes, sir.
And then you will be able to find it in order. How much will be the time cost for finding it?
Degree of VI, like.
The degree of VI,
Yeah.
right?
Yes, sir.
Okay.
Uh-huh.
Good.
Got it. Thank you.
So you can see this kind of advantage of this extra ordering, right?
Yes, sir.
So Akash Kumar Dutta, Harsha Kumar Gupta.
Yes, sir.
So if I give you the extra guarantee that this sets, this adjacency list, this neighborhood is also sorted, how much will you? What will be the time taken for you to check if there is an edge between Vi and Vj?
It will be order of degree of VI. The degree of VI could be.
Degree of Vi can be n in the worst case. But can you do better?
Worst case, it is the same as the
Log Pi.
Who told?
Ujjwal.
Ujjwal, right? Yeah, it will be log di. Okay. Let me see. Somebody else. If somebody can tell me why. Okay.
Binary search.
Okay, good. Yeah, somebody told it already. Yeah, so you can do a binary search. See, once this is sorted and you have to check for whether there is an edge via Vj is in this set or not, you can do a binary search and find out whether Vj is there or not, right?
That it need to be sorted.
Exactly, that's what I told. That if it is sorted for all the, if all these lists are sorted, then okay.
Okay, sir.
If this in the adjacencies list we all have the extra condition that all of them are sorted, then I can find out whether the edge is there in between I and j in just ordered log di number of steps. Okay. Now let me ask you one thing. What about in the adjacency matrix? How much time will it take to check if there is an edge between Vi and Vj?
We go off 1.
Should be just an all constant number, right? Because it's a very ordered set. This is a very well preserved, well ordered thing. So all I need to do is go to the ijth coordinate in this graph and graph meaning on the matrix, and I will output that, and that's it. Right. So more and more the input is ordered and structured, the lesser and lesser work do I have to do, but the input size will become bigger and bigger, and lesser and lesser, and more the input is compressed, right? Even the basic stuff will start taking lot time, but it is compressed, the input is small. So it's a trade-off that is there. So in one extreme, you can think of it that this is the adjacency matrix that is there, and the other extreme is the sets, the edges are there, and somewhere in the middle is the adjacency list. It is pretty good in terms of the compressiveness. It is just less than 2 times the minimum size, and you are not losing too much out. Okay, in the worst case, it can be a log n factor off for finding whether there is an edge or not. Right? So basically from now on, you should always remember that there is this adjacency matrix, the matrix, and then there is the adjacency list. And both of them have their advantages, but usually otherwise stated, I will think of this one as adjacency list. Usually, and this input size will always be considered as this thing. Usually. Okay. Now, a few things that I would like you guys to go back and think about it. So first of all is that if, so these are problems, okay, these are, I mean, maybe I should use a different color. So these are problems that you can think of, okay, that if G is the adjacency matrix, the matrix of a graph, what does G to the power K represent? Okay, what is G to the power K? It is nothing but the matrix multiplied K times. What does this represent? What are the entries of it? So G to the power K ij, what is that? Think about it.
Will it give me a path from I to J?
It will not give you a path, it will give you something of related to the path. Yeah, you're right.
At kth step, we can reach or cannot reach. That information will give.
It will give you the number of such step paths. Okay, you're right. So whoever, if you can think or guess that thing, then you're great. But think about it, okay? For example,
Number of paths of
what is,
length K.
yeah, what is the trace of G cube? Now, okay. So let me just add a few things. So there's something for your just your general knowledge in some sense. And if you guys are interested in this kind of work, then okay, it is not whatever I'm saying now, right now, is not a part of this course. It is actually sometimes I cover in my discrete math course, but this time I have not been able to do that also. But so you have a G which is a matrix. There are a lot of properties of a matrix, right? What does that say? Like, for example, what does the eigenvalues of G represent? And believe me, they represent something very non-trivial. Okay. In fact, the amount of connectivity the graph is, how much connected a graph is, can be seen, can be understood by looking at the spread of the eigenvalues. The other thing is that there are other small things that are there. What if the entries are not just 0 and 1, but I have say -1 and 1 as an entry, or 0, 1 and diagonals are something else. Diagonals are degree. So I can represent this graph with various nice ways. You know, the diagonals we always thought about as 0 because I told a simple graph, so put them 0. But 0 is just a, I mean, it's not giving any extra information. So maybe I can add things like, okay, what happens if in the diagonals I put up a degree of that I, and so on. I get a different graph, right? A different, not graph, I get the same graph, I get a different representation of that graph, a different matrix. What does the eigenvalues of those matrices say? All of these things is something that if you guys are interested, this is an amazingly rich work of literature work is there, and it's an amazingly important problem in many fields of research. Not only just algorithms or discrete math, but in machine learning, huge amount of work was done in this direction. Random walks, kind of this hardcore statistical works that is important, that people do. Pure mathematics in which these things gets connected to other areas like Lie algebras and representation theories in a big way. Then Fourier analysis, harmonic analysis. I mean, this area is superbly vast. And if you guys are interested, feel free to take a look at this. These are called the spectral properties of graphs. It's just basically if I take a graph, look at the adjacency matrix, then what are the spectral properties like the eigenvalues and all those things, what do they represent and what can I get from there and so on. Okay.
Sir, in the first portion, G square means matrix multiplication of G with G.
With G.
Okay.
Yes. Yeah. Okay, because if the n cross n matrix, we'll always get an n cross n matrix only, right? So we can talk about G to the power k for any k.
Okay, sir.
Okay. Now this is something that is something related to various things. I mean, I don't think we have time for any of this kind of stuff. By the way, I should also say one thing, if you guys are interested, that a big chunk of this work was developed and worked on in ISI by a guy called R.C. Bose, one of the great mathematicians or combinatorist of the past century. He did a lot of work in this direction in spectral techniques or linear algebraic techniques in combinatorics, spectral properties of graphs, and so on and so forth. And so, yeah, for the people in the MTech CRS course, they know that the institute that works on the cryptography center here is called the R.C. Bose Center, and this is that guy. Yeah, he has worked a lot on the coding theory, many such areas. Okay, so but okay, as I told you, this part is just for fun, not for fun, but it's for extra knowledge. But this thing, I want you guys to go and think. This first problem that is there. Okay. The second thing that is there is in terms of the adjacency list. Okay. So say if G is given as an adjacency list, C list, can you give an algorithm to order the neighborhood arrays? Okay, so neighbor arrays in an increasing order. So what I mean is that, as I just told you, right, the adjacency matrix is there, right, and then there are these things hanging out from each cell. Now these things are not ordered. Can you order them? Can you give me an algorithm to order them? So if I think of it that this one is written as 1, 2 till n, but this might be given as 3, 10, 2, 1, 9, 5, 10, some kind of stuff like that. Okay. Can you order the edges or order them? Can you somehow give me an algorithm to order them? Can you think about it? Let us all think right now. Can you give me an algorithm? Lakshmikanta Shao?
Some stable sorting into the
This is nothing to do with stable sorting.
because like whenever we change the vertex here, we need to change the order in the next array as well.
Change the vertex.
I'm corresponding index.
I am not changing this. I am not changing this order.
No,
This order is there.
change.
I am just changing each of them. Right?
Okay.
This is not a stable sort kind of stuff. Yeah, think about an algorithm. So if somebody has an algorithm, can you please raise your hand? Some algorithm, any algorithm. Good, bad, ugly, whatever algorithm. Yeah, all of you please try. Okay, so I can see one person has raised your hand. Maybe I can ask. Sujan, you told that you have got this algorithm, right?
Sir, if we do merge sort in each arrays, so will it work? I don't know the correct means it will
Merge
work.
sort in each array. No, I don't understand this one. Yeah, okay, you are merge sort in each array. Okay, very good. So, okay, think about it. What will be the runtime?
Sorting each array.
So, okay, good. So, think about the what is the runtime? Now, think about it yourself. Let other people think a little bit also.
Summation.
Yeah, think about it. Lakshmikanta Shao, are you there? Hello. Okay, I cannot hear you, so maybe there's some technical issues from your end.
It is a complete graph, then merge sorting every list will be costly.
Bit costly. How costly? What do you mean costly?
I mean, every vertex is adjacent to every other vertex. So below one there will be all the vertex. So n log n, and there are total n. So it will be kind of n square log n.
Okay, I mean you are giving me one instance when it is an what thing. I can say input is how much? What is the size of the input? Size of the input is order m plus n. Okay. Now out in terms of this, can you give me some number? Luna, do you have some idea?
So actually, this is like sorting in different arrays. So I'm not getting what is special about this case.
Okay, good. So you're sorting n arrays, right? That's what
Yes.
you're saying. What is the
Yes.
runtime of it?
Yeah, it will be n into n m log n.
Okay, let's see. Okay. N into m log n. Why is it m log n?
N into degree of
Okay, let's see. Okay,
each
so
vertex.
so many of you have been telling. So what you are doing is that you are sorting each of them, right? So to sort any one of them, how much time does it take? If you apply the merge sort kind of stuff like that, how much time will it take?
Log into length. I mean log.
N log n, right?
Yeah.
At most. And it will be taking for all the n of them. So the algorithm that we can think of, okay, so the algorithm one, let's call this one. algorithm 1, this is basically sort each array with a merge sort. Okay, so the time complexity, now what is the time complexity? Time complexity is basically summation of I equals to 1 to n is less than, and each of them will take order of n log n. So this is order of n square log n, right? Again, somebody says, Aditya, you are saying it is for a complete graph. I'm not interested in a complete graph or something. The parameters are two things, n and m. Okay, so let me say it this way, that actually the time complexity is slightly better than n square log n. Why? What is time complexity actually? The time complexity is actually, if you do it correctly, it is summation of I equals to 1 to n order of di log di, where di is the degree of vi, right? So di is the degree of vi. Now, note that this one way of thinking of it is that this di, this is always less than log n. So this is less than summation of I equals to 1 to n order of di times log of n. Now log n I can take out outside, and this will be summation of I di, which is twice m, right? So this will be ordered m log n. Okay. So basically there is a way of getting n square log n, but the same algorithm, when the analysis is done with slightly more finesse, you get order m log n. Again, as somebody pointed out, as Aditya was pointing out, that for the complete graph, you have m equals to n square, and this will be n square log n. But for a non-complete graph, this is better than this, right? Although the algorithms are remain same, but in terms of the analysis, you can see this is better, right? Good. Now comes the question that what I think Luna was saying. Why do you do this, all the simple thing? The simple thing is that it's a question, go and think about it. Give an order n plus n algorithm. This is not, so basically this algorithm is not the best algorithm. You can also get a order m plus n algorithm. Note that order m plus n is better than m log n.
Sir, if there are n vertices, we create an array, 1 to n. So when we are, can you show the picture?
Right.
When we are, at the vertex 1, we just go through the 3, 10, and 2. And just.
Yeah. You are thinking in the right direction. Okay. You're thinking in the right direction.
Yeah, so it will be almost order n plus n.
You have to, yeah. So you don't, think of the right direction, but do it. Okay. It's an interesting. Do this calculation. Yeah, no, not calculate. Write the algorithm. Write the algorithm completely. Okay. So I have already run out of time. I wanted to do something, but which I have not been able to do. But that's fine. This was an important thing to do. So any graph algorithm. So basically, any graph algorithm, we will be thinking of it as either adjacency matrix or adjacency list. Adjacency list, the input is of size m plus n. Adjacency matrix is of size order n square. Okay. Okay. The next thing is that I will not do this today. I think I will stop shortly. Is how to traverse. How to traverse a graph. Okay. So let me ask you a very simple thing. Okay. So say here is a graph. Okay. So by the way, when I will be drawing or explaining, I will possibly be explaining using some kind of diagrams of graph like this. But actually think of it that the graph has been given as a adjacency metric list. Okay. So your algorithm, when you design an algorithm, something of that kind should come out. Okay. So say these are 1, 2, 3, 4, 5, 6, 7, 8. How do I traverse it? Say maybe I start from the vertex 1, then should I now go to vertex 4 or vertex 2? Say I go to vertex 4. Say first I visit this one, then I go to vertex 4. Then which one should I go to? Should I come back and visit vertex 1 or should I go to vertex 5 or vertex 6? Right. And these are the questions that arises a lot. Okay. You have to kind of tell it is not like taking a look at the picture in this thing and say, oh, okay, I can go like this. It is not that. You have to kind of give an instruction to the computer. This is how I want you to go and visit this is how I want you to go and visit all the edges. Okay. So let me tell you a very interesting analogy with real life. Okay. Say you are doing all these courses, the 5 courses that you are doing, right? In each of the 5 courses, there is the introduction chapter, right? In the books and all. And once you are done the introduction topic, there is this saying that, okay, the introduction, there are the subtopics that are there. In each of the subtopics also you can have some more subtopics and so on. Now say if you are trying to prepare for your exam, how will you prepare for an exam? How do you prepare for an exam? Okay, you have to go and cover every possible material that has been done in all the 5 courses. But how will you cover them? Maybe some of them are also connected to each other. Maybe unless you have some understanding of probability, you will not be able to understand something in statistics. Unless you have some understanding of discrete math, you will not be able to do something in programming languages and so on and so forth. Right? They are somehow connected. How will you do that? How do you go by studying? Usually there are 2 different ways of studying, and this is something that we always use. One way is basically what is called, what you can do is that you can go and first do all the subjects, you learn the basic idea. So what is the algorithms courses simple understanding? Do I understand that? Okay, fine, good. The next thing is that, okay, I go to say machine learning. What is the basic understanding of machine learning? I do that. And then I cover all the basic topics, the introduction to all the areas. Then I come back to say algorithms. Okay, now I understand algorithms. Inside the algorithm, there are 3 parts. Say, I will do the 3 parts. I have some understanding of those 3 parts. Okay, good. I have done that. Then I go to the next subject, machine learning. In machine learning, there are 5 parts. I will understand those 5 parts basic and continue like. But inside the 3 parts of algorithms, one of the part possibly has even further subdivisions. There are much more detailed things that you can study. Right? So maybe inside things like a sorting, you have some understanding of what a sorting algorithm is and all those things. But inside the sorting, there are also a lot of 5 different kinds of sorting. Right? So this is one thing that you can do. Right? You can basically have a shallow understanding first of all the subjects, then a slightly more deeper understanding of all the subjects, then the next slightly more deeper, even more deeper understanding of all the subjects, and so on. That is one way of doing it. Another way of studying is that I will take algorithms. Okay, fine. I will study the algorithms in and out completely. I will go into all the subparts and small subparts and understand and do that. Once I'm done with algorithms, I will go to say machine learning, and so on and so forth. Right? These are the two different style of study that you do, right? This is exactly same as in the graph. There are these two standard traversal methods. One is called the breadth first search. Breadth first search meaning you first want to cover the breadth wise, meaning you first travel to 4 and 2. Okay, good, done. I have understood. So I started from 1. I have understood the closer. I have just visited the 2 of my closest ones. Now I go back to say 4, and okay, from 4 I will go to the next closer one, next level. So 5 and 6, I go and visit them, but I don't go further. But 5 and 6 is that distance 2 from my 1. Then come back to 2, and then okay, from 2, which are the 2 areas close by? Okay, there is 5. I have also studied. I have also visited that. But 3, okay, now I visited 3. And then you, okay, so among the set of things that I visited, then I'll go to 6 and so on. So this is called the breadth first search. Of course, this is very quick thing. I will give the more formal definition next class. The another one is the depth first search. Depth first search is, so this is called a BFS and this is DFS. Depth first search is like studying the algorithms course completely first and then go to the next one. So there what you do is that you say first visit 1, then you study, okay, next thing is 4, okay, then 4, then 6, then 6, then 7. I go and try to understand that line as much as I can. Okay, now I have understood 7. Let me come back. Okay, from 6 I can go to 5 and so on and so forth. Okay, from 5 I can go to 8. Okay, good, 8. Now come back. And this is what is called depth first search. So these are the two basic traversing algorithms. Okay, so this is what we will be doing in the next class. We will try to see the actual pseudocode of the depth first search and breadth first search. How do you write the algorithms and so on and so forth, and what are the importance of those algorithms, I mean of this both of them in as an application to some other problems. But basically both of these algorithms will be of a linear time algorithm, meaning the runtime will be order n plus n, and both of them will be used extensively in all the algorithms. So maybe many of you who have done some course in algorithms possibly already know it, but since I know that there are some people who are not from the algorithms or computer science background and all, so you are not that used to these things. Okay, maybe I can have a quick vote of this one. How many people know about depth first search and breadth first search? So how many of you have studied depth first search and breadth first search earlier? Can you quickly raise your hands? Okay, I mean, assuming that the rest of you are not sleeping, it is a small enough number, I would say. So, okay, good. So it is like 1/3 of the class possibly have seen depth first search and breadth first search, but I hope that you will not be bored too much, because we will be doing it as the application of depth first search and breadth first search. And in both of these depth first search and breadth first search, the final output one can think of it as a tree. So you end up getting a spanning tree of the whole graph. Okay, I mean, and spanning tree of the whole graph, and both the trees will have their own importance in terms of properties and all. So, so I will stop today here. I don't want to go too much further into this thing. So basically what we have done is today is we have discussed adjacency matrix, adjacency list, and kind of created our ground for discussing more on depth first search and breadth first search, the traversal algorithms, and this is what we will be doing. In the meantime, think about these two questions that I have given. Okay, for example, say, right, what is the G cube or G to the power k mean, and what is something like trace of G cube, and so on. Okay, and the second is what are design and order, I mean, a linear time algorithm for ordering the adjacency list in a sorted way. Okay, so let's meet again on Thursday. In the meantime, if you guys have any questions, please ask. Any doubts, any questions? And as we discussed, there will be two tutorials, one on Saturday 3 to 5 and one on Monday 3 to 5. Okay.
Yes, sir.
Okay. Yeah.
Got it, sir. Thank you.
Thank you. Okay, good. So I'll see you then on Thursday.
See you, sir.
Yeah. Pallavi Datta, do you have anything to say? You have, your hands are raised.
No, sir. Sorry, I forgot to lower my hand
No,
there.
that's fine. That's fine. Don't worry. Okay.